Now we are going to discuss about the shallow neural networks, basically the earlier version of neural networks, which is based on fewer layers of neurons. The opposite of shallow neural networks is deep neural networks, right? So before we move into the deeper neural networks, where we where the people who are designing the deep neural networks were having some challenges to be facing. So before that, if we learn about the shallow neural networks, we can understand the basics of neural networks, and you will get the understanding how the neural networks are working, how they are making predictions, how they are trained, and in later lessons, we can discuss how the deeper neural networks or deep neural networks are designed based on the same principles of shallow neural networks and how they overcome the issues that are uh, getting uh, increased with the number of layers when the neural networks are made much more deeper, right? And how these issues due to the depth of the neural network are defined are overcome in later lessons. In today's lesson, uh, in this lesson, we are going to discuss about how the basic neural networks are designed and its functionality and how they make predictions and how they are trained, uh, mainly in uh, intuitive sense and also in the mathematical sense. In this lesson, I am going to explain uh, some of the mathematics that are related to neural networks. Basically, you will go through some notations with uh, which are using matrices and matrix additions, multiplications, some general operations that we apply on matrices, and how these matrix operations are used on the learning principles of neural networks. Uh, these are not mandatory for you to use neural networks because most of the existing neural networks that are there in today's world are uh, transparent with these basic operations. Like, for example, when you want to train a neural network, you don't have to think about how the gradients are backpropagated to the previous layers and or how the weights are updated and how to make predictions layer by layer. You don't have to think about that. But uh, in order to get some better insight, we have to learn how these forward propagation and backpropagation operations are working in neural networks. So, and when we are learning the backpropagation, especially we will have to see how these weights are updated based on the gradients that are derived from the uh, loss that you see at the end of the neural network. First, you calculate the loss, and then you backpropagate to adjust all the neurons. That is how it how the how these weights are getting updated in each of the steps. Right. So in the when you are making predictions, what you do, the forward propagation is making predictions. So layer by layer, you can see the neurons are making predictions. And there's a difference between the real value and the predicted value. So that is why the loss is there, right? So we calculate the loss, and this loss is backpropagated to the earlier layers from the last layer, so that the weights of each of these neurons will get updated, right? So with the backpropagation, this is what we do. So the updating weights for the backward side based on the loss function and the loss value is known as backpropagation. And making predictions using the inputs given is known as forward propagation. So when you are training a neural network, backpropagation is always used to update the weight value so that the errors are getting reduced in each of the iterations so that it would go to the optimum weight values. So that means when you are propagating again and again in an iterative way, so your neural network will get optimized to the data set so that the weights will get updated. And once the weights are updated, your neural network is trained. That means it is a learned machine learning model. So this learned machine learning model, which is a neural network, can be used to make predictions by giving some real world X values, and you can get some output from the output layer. As other neural networks are also like other machine learning algorithms. Neural networks are also an approximation function for the real world objects or real world features that we are given and making predictions. Right? So, like the normal neural net, like the normal all the other machine learning algorithms are trained. When you are training a neural network, you are trying to minimize the error. That means you are trying to approximate as much as possible uh, to make predictions uh, closer to the real values or ground truth values. Right? So making prediction is done by forward pass or the forward propagation. Uh, Training is done by back propagation or backward pass. Right? First, we should learn how the shallow neural networks are working. Basically, shallow neural networks are uh, neural networks that are having one or two or very few number of layers of neurons. Right? So we already know that a neuron can be an approximation for a linear combination of x values and weights and a activation function. If the activation function is a logistic function or sigmoid function, that kind of neuron is known as a neuron is actually a logistic regression. Right? So this logistic regression is actually working as a neuron in a neural network which is using logistic function as activation function, right? So there we discussed that we can have some other nonlinear activation functions other than logistic function, and we can change the neurons like in with other activation function as well. However, whatever the neuron we are using, we can combine several neurons into a single layer, and so you can apply such layers back to back and create a multi-layer neural network. Right? When the number of neurons are higher, that would be known as a deeper neural network. Right? So we are going to discuss about first we are going to discuss about smaller or shallower neural network so that we can understand its learning principle, and then we will be moving to deeper neural networks later. This is a single neuron. As we know, in a single neuron, we can have several inputs from these independent variables, and it has a linear combination of these inputs like x1, w1, x2 w2 x3 w3 plus bias or w0, right? And then we apply that value, which we take it as z, and then we can apply it to a sigmoid function or any other activation function, which is generally represented by simple a, right? So once you get the linear combination of input variables and the weight values, you can get the linear combination of input values and the weight values, and then once you apply the activation function for that result, you will get the activation value. This activation value is the predicted value of this particular neuron. So the predicted value is represented by y hat. It can be also mentioned as a because it is an activated value, right? Activation value is the real output of a neuron. This logistic function, if the activation function is a logistic function, we can represent this neuron in this kind of a computational graph. Here you can see that the inputs are x1, x2, x3, same as this neuron, and then we take the linear combination of x values and the weight vector, right? So here what we do is we take the weight vector means is the weights in these inputs, right? The weight of this one should be W1, this one would be W2, this one is W3, right? So there would be another bias value as well, right? So what we do is we take the weight vector and we take the transpose and we take the dot product of this weight vector with the x vector, right? The simple x vector is corresponding to the x1, x2, x3 values, right? And then we add the b, which is the bias of the neuron, right? So let me draw it, right? So this would be bias. This one would be W1. This one would be W2, right? And this one would be W3. This W1, W3, W3 are known as the weight vector. It's x1, x2, x3 can be considered as the x vector, right? In order to take the dot product, we take one of them and take the transpose, and when we make the dot product and we add the bias, which is a scalar value, right? Once we get this z value, we apply this z value to the activation function, right? So this x, actually this x would be equal to z, right? So this sigma function may be the sigmoid function or any other activation function, and then we get this activated value of this neuron, right? This is the same value which is shown as here, right? With this activation value, you can use the loss function and check with the ground truth value or the real value for y and find a loss value, so that you can use this loss value for back propagating, so that you can update the weight values and bias of this neuron. That is how we update a neuron using its learning technique, right? Okay, now let's move into a neural network which has two layers. You can see the first layer is denoted by this notation, the second neuron by this notation, and so on. Here you can see the inputs are given as x1, x2, x3 as usual, and these are the neurons in the first layer, and this is the neuron in the second layer. Actually, you can have any number of neurons in the first layer or the second layer as required, right? Actually, you can have many number of neurons, many number of layers as well, right? Not only 1 and 2, but 3, 4, 5, 6, any number of layers. But for the simplicity for this example, I have taken only 2 layers. First layer having 3 neurons and the second layer having a single neuron, right? Because all these inputs, x1, x2, and x3 are connected to all the neurons in the first layer. This first layer is known as a dense layer or a fully connected layer. Right? And for the second layer also, all the inputs of all the outputs of the first layer are connected to the second layer. So second layer is also a dense layer or fully connected layer. And the second layer's output is considered as the output of the whole neural network, which can be represented by A2, which is the y hat of the neural network. This is the predicted value of the dependent variable or the output of the neural network when we are making predictions or when we are learning. This is the predicted value, right? And it is also equal to the activation of the second layer of this neural network. So this is the second layer, right? So there's only one neuron in the second layer. So A2 is the output of the second layer. So this is the notation that we are using for representing the activation of the second layer. We are always using this square bracket notation for representing the layers by its numbers. We generally don't represent the input as a layer, but if you want, you can consider it as the 0th layer as well, right? 0, right? It's 0 layer. But generally, it is considered as the input, and these layers are considered as first layer, second layer, and so on. So by increasing the number of layers, as you may remember, that we can increase the computation power of the neural network exponentially. For example, if you have 2 3x3 layers, your computation power would be like 3 times 3, which is 9. So that would be equal to having 9 neurons in a single layer, which is equal to having one layer having 3 neurons and another layer having 3 neurons. But in this case, we have only 3 neurons in the first layer and 1 neuron in the second layer, right? For making the neural network simple. So you can have minimum number of layers, and we will be looking at those different types of neural networks that are having different types of neurons as well, right? So the function or the design of the operation in each of the neuron can also be changed from the general notation of the neuron that we are learning in this phase of the lesson. In upcoming lessons, we will be learning different types of units in these neurons. So before that, you just have to remember how an ordinary form of neuron, which is having a linear combination of inputs and weights, is applied to an activation function, and its output is taken as the output of a neuron. Right? In this 2-layer neural network, we can represent the computation graph as this. Here we can see this is the input vector x1, x2, x3, and you can take this x as the x input, and you can update the first layer weight vector and take the dot product of it. So this is the transpose of this weight vector, right? And you add the bias of the first layer, so that you will get the Z of the first layer, right? And then you take this Z value of the first layer and apply it to the activation function of the first layer. Actually, you can represent the activation function of the first layer as well, right? I mean, the activation function can also be changed from layer to layer as well, right? So we can represent the activation of the first layer like sigma 1, right? And once you apply this activation function to the first layer's Z value, then you get the activated value for the first layer. So then you can again apply these output values. So this A1 is actually not a single value because it consists of 3 outputs, right? So this would be a would not be a single value but a vector, right? So then this vector will be applied to the second layer's input. This is used as the input of the second layer, right? So this is the second layer's neuron. So this can have one or multiple number of layers, one or multiple neurons in it, right? So we don't have to mention number of neurons in this notation because we are representing here as in the form of vectors and matrices, right? So we are applying the same rule that we have applied in the first layer, right? So we take the dot product of the weight uh, vector of the second layer, right? Actually, we take the transpose of it, right? Of W2, and then we take the dot product with the A1, right? Like earlier we took the dot product of with X, right? So which is the input for the first layer. In here, we are taking the output from the first layer, which is the activation of the first layer, as the input to the second layer, right? And we take the dot product with the second layer's weight vector, right? So we take the second layer's weight vector, which is W2, and we take the transpose of it and we take the dot product, and then we add the bias of the second layer, right? And you will get the Z value for the second layer as usual, right? So once you get the Z value or the linear combination of the value of the second layer, you can apply it in the loss function, sorry, in the activation function for the second layer, which is sigma 2 in this case. So we can have the, sorry for my handwriting, you can have the sigma 2, which is the activation function for the second layer. And inside this activation function, we can apply the Z2 and we will get the activation value for the second value, which should be same as the output of the neural network, right? With this output, you can calculate the loss of this neural network for the entire neural network by combining it with the real y value or the ground truth y value from the data set, right? So you take the A2 and take the y value from the ground truth value from the data set, and then we apply the loss function. So you know what is the loss function, right? So it can be a mean square error or cross entropy loss or what cross entropy loss or whatever, right? So there can be in type of loss function, and using this loss, you can actually calculate the cost of the neuron, which is the addition of all the data points. Then you get the cost value or using the cost function, and then you can use this cost value for backpropagating this cost to update each of these weights, right? So first we can update these weights, right? And then we can update the other weights of the previous in the first layer, right? If we have any more other layers before this layer, those layers will also get updated. This is the process known as backpropagation. Right? Well, let's move into some notations to get you some understanding about the theory behind neural networks, so that when you are going through some papers or some articles in neural networks in technical form, you will find these kind of notations, so you will understand and you will be able to uh, read these articles and or papers, so that you can improve your knowledge further uh, with upcoming changes of neural networks. So that is the importance of learning these notations, right? So you may not be improving these notations or making some research with these neural networks, or in most of the cases, but if you are going for in that field also, these kind of learning these notations and the mathematics behind neural networks is very important. Even if you are not going into the research side, still you will, it would improve your knowledge with respect to the uh, to its working principles, and also it would open some windows for you to learn more about neural networks in future. Right? So first, let's look at the same neural network, right? So in this case, I have added the zeroth layer, which is the input. Right? So these x1, x2, x2, 3 are considered as the zeroth layer inputs, and then we have the uh, and then we have 4 neurons, right? In the first layer. In the earlier case, we had 3 neurons. In this neural network, we have 4 neurons, right? In the second layer, we have a single neuron, right? So here we have mentioned the outputs of each of these neurons inside the neuron. So the output of the first neuron in the first layer can be represented by A11. That means the first layer's first neuron. So A12, which is the first layer neurons, second output or the second activation. Right? This is the first layer's third neuron output, which is the activation of the third neuron, this neuron, and this is the first layer's fourth neuron output or the activation value. Right? And we take the outputs of each of these neurons, which has these, which have these values, and then we give them to the second layer's input. Right? If we had any other neurons, we would have to give these outputs into those neurons as well. Right? For example, if we had another neuron like this, we would have to give the inputs like this. Right? So I am just giving you this example for much more clarity. Right? So then that neuron will also have an output likewise. Right? So it can have more than 2 or 3, 4, or a number of neurons in the second layer. But for the simplicity, we haven't added those kind of neurons, but only a single neuron for the simplicity. Right? Sorry. Okay. So in this case, you know the input x1, x2, x3 can be represented as x, right? And the z values for each of these neurons are calculated like this. For example, for this neuron, this is how we calculate, right? For this neuron, this is how we calculate the z values and a values. This neuron, this is how we calculate, and this neuron, this is how we calculate, right? In here you can see this x1, x2, x3, the inputs in the 0th layer, it's not actually a layer, but it is the input, right? We take them as an x input as a single vector, right? So then we for in the each of these lines are corresponding to each of the neurons in the first layer, right? So what we do here is we take the weight vectors of the first layer and take the dot product of it with the input of the input, right? And then we add the B1, that means B11, which is the bias of the first layer, first neuron. And once we get this, and once we get the Z11, we can apply this Z11 into the activation function of the first layer. Actually, we haven't specified that explicitly this is corresponding to the first layer, right? So all the other neurons from this sigmas also, you can actually have the sigma 1 as the activation function, right? So generally, in this case, we assume that we are using a logistic function or something, right? So that's why we haven't added the first layer as this notation, right? But actually, you can have different activation for different layers, right? So once you apply the activation of the first layer to Z1 of the first neuron, then we get the output for the first neuron of the first layer, which is A11, right? So you can see this is the same value as this value, right? So here what we do is we take two steps, which is first one is we calculate Z11 and then we apply it to the activation function of the first layer. Then we get the A11, which is the output of the first neuron of the first layer. Similarly, you can calculate the Z values for the second neuron of the first layer, and then we apply it to the activation function of the first layer, and then we can get the activation function of the first layer second neuron. Similarly, for the third neuron also, you can calculate, right, the Z31, which is the Z31, which is the activation, sorry, which is the linear combination of third neuron of the first layer, and then we can apply it to the activation function, and then we can get the activation output A31, which is the out value, which is the output of the first layer, third neuron. Similarly, for the fourth layer, for the fourth neuron of the first layer, you can get the Z41, and the Z41 we by applying it to the activation function, you can get the activation value for the fourth neuron of the first neuron. And these are the outputs, right? The values that I have just circled, right? So these are the outputs of each of these neurons, and then we take these outputs to the second layer, right? And then we apply the same set of equations for the second layer, which are applicable for the second layers, right? So for the second layers, this W vector would be different because it will be a different value for the second layer, this neuron, right? And for the activation, it would be same, but because there's only a single neuron, it would be it can be actually represented by sigma 2, right? If you want to represent it as a activation function for the second layer. So once you apply these inputs to the and get the Z2, sorry, Z1, 2, right? Then you can apply it in the activation function, and then you will get the activation output, which is the A2, which is the output of the whole neural network. Right? In this two-layer neural network, this is known as the input layer, and this is known as the output layer, because this is the layer which is giving you the final output, right? And any other layers that are in between input layer and the output layer will be known as hidden layers, right? So there's only a single hidden layer in this neural network, right? Now let's move into further into this two-layer neural network for neuron vectorization. So what does it mean by neuron vectorization? In this case, we find that we have 4 equations for each of these neurons in the first layer, right? So actually in this case, we are not specifying, we are just limiting to the first layer neurons, right? So we have 4 neurons in the first layer. Because of that, we have four lines. Actually, in one line there are 2 equations, right? So Z value and the activation value, right, for each of the line. And but if you, because we want to calculate these calculations faster and in parallel, we can use these values as vectors like this, right? And we can do the calculations in parallel, right? So in this case, we can take these W values of this, of all the 4 neurons as a single vector, right? And this X value, actually, this is already given as a vector, right? So this X value can be represented by this vector, right? It is already represented as a vector. And all the bias values for this particular layer can be considered as a vector as well, right? You can find this B11, B12, sorry, in whatever we say, right? So first we can say, tell the layer number first and then the neuron number. If that is the notation we use, we can use B11, B12, first layer, first neuron, first layer, second neuron, first layer, third neuron, first layer, third, fourth neurons, bias, right? These are the biases of each of this neuron. These are the weight vectors of each of the neurons, right? So now you can see these are vectors of vectors when it comes to this vector, right? And once we apply this value, you can get the Z vector, right? So this is also a vectors of vectors, right? So inside W, these are vectors, and applying to these ones, you get vectors, and this is a vector of vectors, and it's kind of matrix, right? And once you apply this Z1 to the activation function, like this, right? You can get the activation values as a set of, you can get the activations for all of these neurons, and we can take it as a single vector known as A1, right? So this A1 is actually the vector of all the activation outputs of all the neurons in the first layer, right? A11, A12, A13, A14, right? A11, A12, A13, A14. These are the activations of the first layer that you can get from this neural network. So this vector representation can be further calculated for the second layer as well, right? For the first layer, you can calculate the Z value, Z1, which is this value, can be calculated by taking W1. So W1 is actually this specific value, right? This is the capital W1. And W1X, you know what is X, right? X is this is the X. And the X, and then this is the bias vector for the first layer, which is the vector that we have just found, right? Which is B1. Once we get this matrix, right? So this is a vector of vectors, right? So this one can be applied to the activation function for the first layer like this, and you can get the activation function, activation output for the first layer, right? So this activation output for the first layer can be taken the dot product with the weight matrix uh, that you can get for the second neuron, which we haven't shown here, right? Because up to now we have calculated everything for the first layer only, right? So similarly, you can intuitively understand that you can get the this is for the first layer weight matrix. Similarly, you can get the weight matrix for the second layer as well, right? So you can take the dot product of this second layer weight matrix with the output of the first layer, right? And then you can add the bias for the second layer, which can be also analogous to this B1, right? So because there's only a single neuron, it would be only a single value, right? So not many values, right? For the WT2 also, there won't be many W values. It wouldn't be a vector, but it would be a single value, right? Like W2 transpose, right? Similarly, you can calculate the Z2, right? So the linear combination for the second layer, and that value can be applied to the activation function for the of the second layer, right? So this is the sigma 2 actually, right? So this is sigma 1, right? I'm not specifying always. And once you apply the activation function for the second layer, you will get the activation output for the second layer, which is the output of the whole neural network, right? Which can be represented as y hat, right? The predicted value of the neural network, right? Okay. So now let's move into further complexities, right? So I think you guys are okay with the current uh, explanations. So up to now, what we have done was we have calculated the first we started with the single neuron, and then we went to multiple neurons, right? And then we calculate for the multiple layers, right? And now what we are going to do is we are going for multiple data points for the neural network, right? So up to now, what we have done was calculating the values for a single data point input, right? So when you get a single x vector like x1, x2, x3, you can calculate the y hat value uh, like we have explained up to now, right? This is how we calculate the y hat value for a single data point, right? Now we are going to expand this statement, expand these equations for multiple data points as well. So here we are going to define two new, much more uh, uh, generic form of matrices known as Z and A, represented by capital Z and capital A. Right? Actually, you can now get some intuition, right? So this is a capital Z is the extension, a generic form of simple Z, right? So this capital A is actually an extension of simple A, right? So you'll see what they are. So now we are defining two matrices where each column in them are corresponding to Z1 and A1 respectively. Right? So if you take a capital Z matrix, its columns would be like Z1 right? Z1, Z2, and Zn, right? When there are n number of layers in the neural network. Similarly, if you can have we can represent the A matrix as so you know how you get the A value, right? So for example, once you apply the activation function for each of these Z values, you can get the activation values for the first layer, activation value for the second layer, and activation value for the nth layer, right? So each of the column in the capital A matrix would be representing the A1, A2 up to AN, right? This is the new notation that we are taking, right? For ZNA, each of the data points of the sample is corresponding to each of the row, right? So when you take this Z matrix, each of the data points are corresponding to each of the rows of the Z matrix, right? It is similar to the A matrix as well. Each of the rows in the capital A matrix would be corresponding to each of the data points, right? So this is a much more generic notation. So this would be like capital Z would be like vectors of vectors of vectors, for example. A can be also considered as the same, right? The only difference between Z and A is that you get the A once you apply the activation function for each of these columns with each of the activation function corresponding to each of these columns, right? So by applying the activation function for the first column, you can get this column. After applying the activation function for the second column, you can get this column. For the last column, you can get the last column of the activation function. You apply the sigma for each of the layer, right? So this if you think about rows are corresponding to each of the data points for both Z and A, capital Z and capital A matrices. So now you will understand that this notation seems simple when we are writing it in the book or paper, but actually this is a very complex data structure, right? So I said this capital Z, for example, is a vectors of vectors of vectors. So it may be at least three-dimensional data structure. So when something is having much more dimensions, that means its data content is increasing exponentially, right? So for example, if you have a single dimensional vector and you are making it square, right? When you're having 2 dimension, so its data requirement is getting quadratic, and when you are having 3 dimensions, it would be cubic, right? So you will understand that when you are having higher number of data points and higher number of features in this for this particular application of the neural network, you would need a lot of memory and lot of computation involved when we are doing the calculations, right? So that is a problem if you want to do it in a sequential computer. That means if you have a very complex data cube like capital Z and capital A, that would not be easy if you are doing the these mathematical calculations one by one using a sequential computer, right? Because of that, you should have a parallel processing computer, or which any computer which is supporting hardware, right? Hardware acceleration we call, where you have the support like uh, by parallel processing hardware like GPUs, right? So in some of the CPUs, there are some internal GPUs, or these days NPUs, like known as neural processing unit, or there are uh, Google-based specialized hardware known as TPUs, known as tensor processing units. And in NVIDIA, they have specialized DPUs known as data processing units. All of those are specialized hardware for executing complex vector calculations uh, in parallel uh, to reduce the time it takes to do the calculation. Right? So when we are working the real world problem with using a neural network, these days you not be able to do it using a CPU, other than if it is a very simple problem. If you are doing something serious, you would need the support of GPUs, or NPUs, or TPUs, or DPUs, or any other hardware, specialized hardware support for processing these uh, vector, or in general tensor calculations in your computer, right? This is something that you have to know when you are really using, when you are training, or you are running, making predictions using neural networks in a computer. In this example, you can see how a sequential neural network values are computed in the forward propagation, right? So you start from the first. Actually, you can see here you take M as the size of the uh, data set, right? And you start from 1 and up to M. You take I value, and this is how you represent the notations related to each of the data points, right? So next to the layer number, which is given in the square brackets, you give the you put these parentheses, and you put some number, which is the data point count in this notation, right? So this is the notation that we are using in the future as well, right? In this case, you can find for the ith data point, right? This is 1 to M means we are traversing through all the data points or in this data set, that this training data set. And for each of the data set, you're calculating the Z value using this capital W matrix, which we have just discussed above. And you are applying the ith X value. That means ith data point ith data points related X values as a vector, and then we use the B value for the first layer, and then you calculate the Z value for the first layer for the ith data point, and then we apply it to the activation function for the ith layer, sorry, for the first layer, right? Activation function for the first layer, and then you can get the activation value for the first layer for the ith data point. And when then we apply it as the input for the second layer's input value, right? And then we use the capital W2 matrix, which we have just discussed, and using this matrix multiplication plus the bias value for the second layer, this is also a vector, right? So then you can get the Z value for the second layer for the ith data point. So similarly, then you can apply it in the activation function for the second layer. And then you will get the activation value for the second layer for the ith data point, right? So everything that we have learned about here is described for the ith data point, right? So I think you can remember that we have just discussed all these steps for in general, right? So but here we are explaining it for the ith data point, which is the same, right? So what we have discussed is actually relevant to a single data point, right? So when you are using a for loop, this is how you have to implement it in a code, right? So this is not actually a code, but this is a kind of notation that you can understand how to traverse through all the data points in the data set, right? So this would be like training for, this is like you are calculating these values for all the data points individually, right? So what in the real world, you are maybe using a mini batch for calculating this, right? So, but now you can see it takes a lot of time because we have to pass through all the data points as well, right? So for all the data points, you have to calculate this W values, and so, but you can use the Z vector, right? So is the vectorized implementation for all the data points. So instead of using applying these equations for all of these data points individually, you can apply it in a single matrix using this capital Z notation, right? You can use applied capital Z1 is W1 capital capital W1, which we have discussed just now, and then you can get the X values, right? Capital X plus B1 for the first layer, and then you can apply it to the first layer activation function, and you will get the activation matrix for the first layer, and you can apply it as the input for the second layer, and then you can use this capital W matrix for the second layer, and add with the bias for the second layer, and you will get the Z output for the second layer and apply it in the second layer's activation function. You said sigma 2, right? And then you will get the A2, which is the matrix corresponding to the output of the second layer, right? If there are only two layers, this would be the this may be the final output, which is the y hat, right? Otherwise, it may be this output of the second layer can be used as the input for the third layer, and so on, right? So in this case, you can find this X value, this 8X matrix, which is introduced just now, can be represented as a matrix for each of the data points, right? Like we said that for capital Z and A, we can have X matrix for all the data points, and for each of the data point is corresponding to the column of this capital X matrix, right? So this is the Z1, that means capital Z value for the first layer. So when you say capital Z, that means for all the data points, right? When you say capital X, that is for all the data points. So when you take capital Z1, it is simple Z first layer, first data point, first layer, second data point, and first layer M data point, right? For the activation, the same is applied. Capital A1 means the first layers, capital A means first layers activation for the first data point, first layers activation for the second data point, first layers capital activation for the mth data point, and so on, right? So these activations are given as columns for the capital A matrix. So this is the notation for capital A that we have used here, right? This is the Z value that we have used here, right? Z is this one, A1 is this one, right? X is where we have used the first input for the neural network. Okay, now we have discussed how we calculate the values for uh, one by one uh, through in the forward propagation, how you calculate these values, right? So when you are applying the activation function, we have just discussed about uh, sigmoid activation function, which is an activation function uh, which is having this is 1 and this is 0, and if this is 0.5, and if this is the border point, and this sigmoid function would be something like this, which is between 0 and 1, right? At the 0 point, uh, the z value, or the sorry, the output value, activation value would be 0.5. This is the nature of sigmoid function. But this sigmoid function is not that working really well for neurons that are inside the neural network, right? So we later we will discuss what is the reason. But now what we have to understand is that sigmoid function is not the best function to be used as the activation function of a neural network. So this is the tanh function, which is an alternative function for this sigmoid function, which has the following equation, right? This, if we are using tanh as the activation function, this is the equation that we have to use. E to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z. So this would be ranged in between +1 and -1. At the 0, the value would be 0. Because this tanh function is symmetric uh, in 0 point, this is a good function to be used as activation function, better than the sigmoid activation function. So this was proven with experimental evidence, and people have started to use this function instead of sigmoid function later in the neural network development. So what do you think? Does sigmoid function is sigmoid function too old, or isn't it used anymore? I mean, are we only using tanh function, and can we forget about the sigmoid function? Actually, not. In neural networks, when you are having a regression output, like if you want to have binary classifier, right? If you want to design a binary classifier, which would be having 0 and 1 as the output values, you can use sigmoid function as the output for the output layer only, right? So suppose you have multi-layer neural network, uh, first layer, second layer, third layer, and so on. And we have input x values in first layer, second layer, third layer, and so on. If this is the last layer and we get the uh, predicted value, this is the last layer, you can use the sigmoid function only for this last layer only, right? For all the other layers, you have to use some other better activation function like tanh, right? actually tan h is not the best activation function that you can use. So we said sigmoid function is not good because it is ranging between 0 and 1. The tan h is better because it is ranging from positive +1 to -1. But still there is a problem when it comes to larger neural networks known as the vanishing gradient problem. That means when you are having deeper neural networks, which we are not going to discuss in this lesson, when you are having vanishing gradient problem, you would have to think about this vanishing gradient when the value is too small or too large, right? So when the value is around 0, you can see there's a variation in its value in this range, right? However, when the value is too large, somewhere here, or the value is too small, somewhere here, you can see there is no change in the value when the x value is changing. Or if this is the z value, right? The tan h value, tan h z is, this is tan h z. Tan h z is not changing at all when the value is too small, x z is too small or z is too large from in size, right? It is a too small to, that means a larger negative value or larger positive value, the tan h value will not be changing. Because of that, when you are backpropagating through the neural network, these changes will not be propagated well for the later layers. So the earlier layers, that means, so these layers will be okay, but for these layers there would be a learning problem because we cannot get a proper gradient. So because these vectors, these weight vectors will be updated in the gradient descent based on the gradients that we calculate, which we are not going to discuss how the gradients are getting calculated because you would need calculus for calculating the gradients in each of these formulas, right? So when you get the gradients, these gradients will be used to update the weight matrices. So these values would be very small when this gradient is very small, right? Because of that, this tan h is also, tan h function is also not a good option like the sigmoid function. Because of that, we can use a better activation function known as ReLU activation function. This is known as ReLU, which is known as the rectified linear unit, where it is having this characteristics, where this is the 0th value and this is the ReLU value, right? This is the positive side. So if the value is positive, this y value would be, say, x-axis would be same as the, sorry, y-axis same as the x-axis, right? To get this value, you get the same value here. Get this value, you will get the same value, right here. So this ReLU function is known as the max of 0 and x, right? If it is greater than 0, it would be, the output would be same as x. If it is lesser than 0, that means if the x value is negative, the output would be 0. You may think why we call it as a nonlinear function, actually, or whether it is a nonlinear function. Actually, this is nonlinear because this is linear only when the value is greater than 0. When the value is lesser than 0, it is different, right? So because of that, this whole function this whole ReLU function is not a linear function. It is linear only in the positive range. This ReLU function is the best function uh, or the first known best functions, activation functions that can be used inside the deep neural network. So instead of using tanh functions, actually you can use ReLU functions, which is computationally also it is very cheap compared to tanh function, and you can increase many number of layers and increase the depth of the neural network without much issue of the problem known as vanishing gradient problem, where the gradient is getting lesser and lesser so that the uh, deeper layers can't learn properly. Right? So this will not happen because always the gradient is 1 when the value is greater than 0 for the ReLU activation function. And also it can learn faster because these gradients are not getting reduced uh, because always the value is always the gradient is equal to 1 when you are back propagating through these kind of neural layers, neuronal layers. So these kind of neural networks can learn much faster than the neural networks that are using either tanh activation function or sigmoid activation function. Okay, so to now I have explained that we can use uh, neurons in layers, and for the last layer it is okay to use sigmoid activation function, but for the other layers you can use other activation functions, especially the ReLU activation function, right? So earlier I said that you can use tanh activation function, but later I said that tanh is not the best one. The best one is ReLU, right? Actually, there are some variations of ReLU activation functions as well, but ReLU is generally okay for almost all the cases in general. With empirical evidence, ReLU is the de facto solution for the activation function inside the neural network. So, why are we always using activation function? Second activation function. All the neurons in the neural network. Can't we simply ignore the activation function and use the linear combination only? That means use the Z value as the activation value. Is that okay? I mean, by just looking at this ReLU activation function also, you may get that idea, right? So why do we use this value, or why can't we use an activation function like this? So if this should be 0, right? Why can't we use an activation function like this? Which is the same value, right? So without using an activation function, you can use the linear combination directly, right? But the problem is that when you are using linear activation function or without using any activation function at all, without any activation function, your whole neural network will not be working as we expect it to perform. That means when you are having many number of neurons and many number of layers, what you expect is that each of the neuron in the neural network is doing some distinct uh, distinct learning process, which is adding some value to the neural network, right? But unfortunately, if you are using a linear activation function or no activation function at all, this whole neural network will be equivalent to a uh, single layer, uh, to a very simple neural network, right? So So it would be equivalent to the linear output of the inputs, right? So although if we are using many number of neurons with many number of layers, right, and get the output, so many number of inputs and many number of layers and get the output. But if these input layers activation function is equivalent to is same as the uh, linear function, or there's no activation function in these layers, this would be equivalent to a single neuron with no activation function output, right? So this would be equivalent to a single neuron which has x1, x2, x2, x3, xn, and y hat, which is equal to wtx or wtx plus b, right? So although you are using any number of layers and any number of neurons, if you are not using a nonlinear activation function for the internal layers, mathematically we can prove that it is equivalent to a single neuron without any linear activation, without any nonlinear activation. So that means it would be equivalent to a linear combination of x values and a weight vector, right? This is not what for real world, right? If you want this kind of behavior, you can simply use a linear regression, right? Or something like that, right? But we are going to a neural network to have much complex learning process, so that you must use a nonlinear activation function like the ReLU activation function in the internal nodes. For the output node, you can either use a nonlinear output or simply use the linear output as well, or you can use sigmoid activation as well, right? So you can use the linear output when you are using it for regression, right? Actually, you can use the sigmoid activation when you are using it for binary classification. When you are using it for linear regression or some other any form of regression, you can use a linear output for the final layer, but in but for the hidden layers and the input layers, you have to use nonlinear activation functions. So these are some of the this is how we calculate the derivatives of each of these equations of the linear sigmoid tanh and ReLU activation functions. These are the equations and these are the derivatives, and these are the gradients that we have to calculate for each of the steps. We are not going to discuss how these are calculated because it is difficult, and also remember that you have to do the random initialization. Otherwise, for the weight vectors in the neural network, otherwise, if you are using zero initialization for the weight vectors, as all the values will get updated simultaneously. That means all the zeros will be updated in a same value. Adding multiple neurons in the neural network will not matter because all the weights will be the same, similarly updated, right? For example, if you say that there's a neuron and it has a weight value 0, and this weight value is also 0, this weight value is also 0, this is the output, and if we add some small change like 0.5, 0.2 or something, this one will also become 0.2, this one will also become 0.2, and so on. So all the time, if we have started with 0 for all values, for the initialization, then these neurons will be for all the weight values for this particular neuron. Every time it will be acting as the same, right? If all the neurons are having uh, zero initialization. So because of that, you have to initialize each of these weight values in random values, right? And start the learning process so that it will be learning properly. So this is a simple code where you can see that here we are using random normal distribution for initializing the kernel, and there are some other initialization codes, initialization techniques known as Glorot uniform initialization, which is based on the Xavier initialization, which we will maybe discussing later, which is somewhat different from the random initialization. And there's another form of initialization known as HE initialization based on the which is good for the ReLU activation function. And this is how we write a simple code with TensorFlow for neural networks. So if you have time, you just go through this one. And this is an example how you can get the image and you convert it into pixels of 487 pixels, and each of them are connected to some other hidden layer neurons, and this is the output layer. So we are going to classify whether these images belong into any of these classes, right? From 0, 1, 2 to 9, 1, 2, 9. So for all the 9 numbers, we are trying to find which digit does this input image belongs, right? For all the image pixels are mapped to this input, right? And each of these inputs are mapped to the inner neurons, and these neurons are mapped like this, and they are finally mapped to the output layers, right? So for all the white dots, relevant neurons will get activated and they are passed to the forward propagation, and they will be learned in this format. So this is how the forward propagation works. We haven't explained how the back propagation works, right? So there are many forms of neural networks, not only the feed forward network that I have just explained, right? So you have this is the simplest one, single perceptron, and this is the one that we just explained, the feed forward neural network. So there's another form of known as somewhat different form known as radial based networks, which we haven't discussed. So when you have many number of layers with many number of connections, which is known as deep feed forward networks. And we are not going to discuss all of these neural networks now, right? So there are some loop connections in some neural networks known as recurrent neural networks, LSTMs and GRUs. And there are some neural networks that are having smaller middle and larger inputs and outputs, known as autoencoders. So there are some different forms of autoencoders known as variational autoencoders, and denoising autoencoders, and sparse autoencoders. And there are some other forms of different types of neural networks like Markov chain, Hopfield network, Boltzmann machine, restricted Boltzmann machine. Actually, this restricted Boltzmann machine was the initial form of neural networks that were designed for back propagation, right? So, and there are some other forms like deep belief networks, deep convolutional networks. So we will be discussing later about this deep convolutional neural networks, right? And we will be discussing about the deconvolutional networks in the generative AI lesson, and there are some other forms of neural networks as well. And there are generative adversarial networks, which we'll be also discussing in the generative AI, right? And the latest one is known as the liquid state machines, which may be in this semester, this time we will be discussing about this one as well, where the internal nodes are randomly organized. The similar kind of one is known as extreme learning machines, and there's another one known as echo state network, and so on. So there are different forms we are not going to discuss. Deep residual network, differentiable neural computer. We are, instead of using distinct layers, we can have we can model it as a continuous function, and perform the learning. And there's another form known as neural Turing machine, where we are mapping everything. So it's a different one. So we will not be discussing it here. The capsule network, which was found by Geoffrey Hinton, who invented the this one this backpropagation. So it's another form of an advanced form of convolutional neural network. So we may not be discussing it in these lessons. And Cohona network is a bit older network form. It was used in self-organizing maps, which we are not going to discuss in this one. Sorry. The attention networks, there are another form. And that's all for today's lesson. If you have any questions, you can ask.